Welcome. Let us talk about intelligent games. In artificial intelligence, when it was invented, these artificial intelligence was only meant for different strategic problem solving and decision making. Among the different strategic problems that is dealt in artificial intelligence, game were one of those. Mostly, we talk about two-player games in artificial intelligence. And in today's lecture, we will see that how strategic problem solving can introduce or can be introduced in game solutions. In a strategic game, a game is expanded through a game tree. A game tree also is known as an AND/OR tree, where OR nodes are represented by square and AND nodes are represented by circle. So if we try to look about the OR nodes, so these OR nodes are specifically represented by the square symbol. And when we talk about the AND nodes, these AND nodes are represented by circle. These square nodes, they always try to maximize the value of the game, and these circle, they always try to minimize the value of the game. In subsequent lecture, we will see why or how we can state that how the game tree values can be maximized or minimized. However, in a two-player game, one player is implemented as a maximizing player and another player is implemented as a minimizing player. Within the game tree, each of these players look for their winning strategies, and their winning strategies means they will try to optimize their objective, which means the maximizing node will try to maximize the value of the game tree and minimizing node will try to minimize the value of the game tree. Furthermore, we will see that in an AND OR nodes, they appear at alternative levels of the search tree. So this is one example of a strategic game where we can see the root nodes, which is an OR node, which represents a maximizing ply, and the subsequent level 1 nodes, they are representing the minimizing ply, and they are the AND nodes. Here, henceforth, we can see that level 2 is again a maximizing node, which are represented by OR nodes. Level 3 is again a minimizing node, and again level 4 is a maximizing node. Now here you can significantly see that within the game tree, if we try to follow the structures, then here you can see in this particular portion two different maximizing nodes are in the lift level, and they are representing, the first one is representing loss and the second one is representing the winning strategies. Now whenever they are merged to a minimizing node in this way, so minimizing node will try to select the minimum value in between those two options. Here in between loss and win, we will say the loss is significantly a minimum value and win is significantly a maximum value. Accordingly, you can see at the other level or in the other portion of the node, you can see in between loss and draw, it has chosen loss as because the draw is again a better value than a loss. So always the minimizing node will look for the minimum value. Simultaneously, whenever my penultimate level is a maximizing level, then say if I take this particular example, here you can see with respect to this particular node, we have one option as a loss and another option as a draw. And in between loss and draw, since draw is a better option than loss, so the maximizing node has tried to select draw as an option among the leaf levels. Based on this particular strategy, if we look further, then you can see that here comes a minimax algorithm. In this minimax algorithm, you can see the root node, it is starting with an AND node, Then subsequently we have OR level, then again the AND level, and the leaf nodes is the OR level. In the OR level, we are having some values over there. Now in a minimax algorithm, our basic purpose is to check what will be the value at the root for this particular tree. So again, if we go back to the board, we can see that for such a particular game tree, when we take this particular example, so let us talk about the initial portion. In this initial portion, for this particular node, which is an AND node that has got two different options, 10 and 11. In between 10 and 11, obviously we can understand, since the 10 is a minimum value in between these two, so these particular AND node will select 10. Simultaneously, for this one, it has an option 9 and 12. In between 9 and 12, since 9 is a lesser value, it will select 9. For this particular node, it has two options, 4 and 20, so it will select 4. For this particular node, it has 9 and 15, two values as an option, so it will select 9. So here you can see a minimizing node always will take the minimum value out of its options under the following level. Now again, at this particular level, you can see we have two different nodes and both are OR nodes. Now the OR node at this particular juncture, if we take this particular OR node, so with respect to this OR node, we have two different value options selected under, and one is having 10 and another one is having 9. So in between 10 and 9, since we know that the OR node is always a maximizing node, so it will select 10 automatically. Over here we will get 10. Simultaneously, if we talk about this node, it has got two different options, 4 and 9. So in between this 4 and 9, since 9 is a higher value, so it will take 9. Now coming back to the root level, which one is an AND node? And under this AND node, we have two different values selected by the OR nodes, that is 10 and another one is 9. Since we know the principle of the AND node is always to select the minimum value out of this, so it will try to find out 9 in between 2, since among 9 and 10, 9 is the minimum value. Subsequently, the same strategies are followed if the values are given in terms of an alphabetical order. In alphabetical order, we know A is the minimum value and Z is the maximum value. Z is the maximum value. So accordingly, if we talk about this particular point, then if we deploy an AND node, and within that the subsequent level should be have the OR nodes. So in this AND node, under this AND node, if we have two different options, say one is M and another one is say U, among M and U, since M is less than U as per the understanding, so this AND node will always select M from its option. In reverse, if we have an OR node situation where an OR node is having two different AND nodes under this, and these two AND nodes are having some values like say F and Q, and since we know Q is greater than F, so this particular node will select Q. So far in this example, whatever the trees we have considered, we have seen for all such trees we have only options for two different branching. It means from one particular node we are getting out two different branches. But always, depending upon the strategy and logic of the game, it may not be like only two different branch. In some cases there may be no branching depending upon the logic. In some cases, there may be two branching or there may be many branching. Following that particular principle, for one particular node, if it is an OR node, it may have multiple AND node underneath of this, and these AND node may have different values based upon the logic of the game. Simultaneously, this can be reversed also, like a particular AND node can have many OR node under this. Now, the same minimax strategy, if we apply over here, these OR nodes, certainly they will have some values, like say 5, 15, 7, 10, and 2. Now, among these all possible options, 5, 15, 7, 10, and 2, we can see that 2 is the minimum value. So, as per the strategy of the AND node, it will always select the minimum value out of all possible options. So by this, you can understand that in reverse situation, if there be an OR node, then also that OR node, if that has multiple AND nodes underneath it, then from all possible AND node, it will try to select the maximum value which is available. Say this one is having 71, this is having 52, this is having 32, and this is having say 101. So among all these values, since 101 is the highest value, so this node will select out 101 as a part of it. So hopefully we have culminated the idea of a minimax algorithm by now, and based on that we have taken out this particular solution which is already discussed on the board. Now you work on this particular assignment. Here in this assignment you can see all the leaf nodes are populated with some values and their penultimate nodes are not assigned with some value. You have to apply the minimax strategy in order to find out the ultimate value at the root. Similarly, we have taken another assignments where in the same graph the leaf nodes are populated with some letters, and depending upon the alphabetical chronology, we need to apply the minimax strategy over here to find out the value of the root. Further, in a real life application of this minimax strategy, one of the popular game that we'll be discussing about, that is the tic-tac-toe game. So in a tic-tac-toe game, you all know that we try to work out with a 3x3 board where we have two different players. One player try to proceed with the cross symbol and another player try to proceed with the circle symbol. So let us assume the cross symbol is the maximizing player and the circle symbol is the minimizing player. Here, whenever we start the game, so this particular game, it follows a different strategy in order to evaluate the conditions of the board. So here you can see, if we draw this board and if we try to start with this cross, now significantly this cross, putting the cross over here, it is equivalent to three other board positions. How they are? So let us check. This board is equivalent to this board position also. Whether if we try to put a circle rotation of this particular board, then actually it is reachable to this particular situation. Simultaneously, it is also similar to this and it is also similar to this. So it means if the first player who is playing with the cross symbol, and if he try to put the cross symbol in any of these corner position, then whether he marks over here or here or here or here as an initial strategy, all these four board positions are similar. So in order to simplify the game logic and in order to proceed with the game tree, we will take any one of these board position as one of the move for the cross player. Simultaneously, if we move into other direction, you can see that instead of corner position, what are the other position the board player, the cross player can put in. So actually, if I take the board, so there are 9 different possibility to start the game. So this 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are 9 possible options through which the first player can take any one of these 9 positions and can start its game. So initially what we see that if a player marks here, so if that is one option, so simultaneously by choosing this option he is also covering option 2, 3 and 4, these all options. Another, let us check what are the other equivalent position. So if he desires to marks over here, so this is an unique position, it has got no equivalent location, the central position is unique. Now instead of the corner or the central position, instead of the corner or the central position, if he attempts to marks over here, this is again equivalent to marking here or here or here. So which means in a tic-tac game, if a player desires to mark over here, that is similar of marking here, also similar to marking here and also similar to marking here. So by now we can see, so just by 3 different moves a player can select all 9 positions in order to proceed with its initial game. So let us check, suppose he marks here, so by now he covers these and this. If he marks here, so this is a unique position. If he marks here, then this is actually equivalent to this and this. So now you can see just by taking 3 different moves, the first player can cover all 9 different positions. Now at the next level, with respect to each of these positions, so let us first analyze this particular board. Similarly, we will get that for the second player also we have a certain identical position where we need not to mark all the game situations. Just by marking some of the board positions we can cover all the possibilities and we can check that. So let us see, as a part of reference we have taken this. So now comes the circle. So if he marks here, as we all know, so this is one unique position. Otherwise, or the second player may select to circle here, which is identical to this, or the second player may select to circle here, which is identical to this, or the second player may select this position, which is the just opposite diagonal, and this one is the unique position. And finally, there is one more option, that is, if the second player try to opt here, then this is also similar to this position. So since we have initially seen, so there are 9 possibilities of marking altogether, but considering already cross has marked in one cell, so remaining we have 8 position. So this is 1, this is 2 and 3, this is 4 and 5, this is 6, this is 7 and 8. So all 8 different positions are covered over here just by one move, two move, three move, fourth move, and fifth move. Simultaneously, if we go back and if we try to analyze this particular position where the cross player initiated with the middle location, then we can see if the circle player marks over here, so that is similar to these, and this position. Simultaneously, if the second player who is playing with the circle marks over here, this is this, and this position. So altogether, it covers 1, 2, 3, 4, 5, 6, 7, and 8. So all 8 different locations are covered by this marking. So whenever you will be expanding the game tree, you have to logically analyze the games and minimum number of moves you need to show, which will cover all possible moves by a particular player at a particular level. Now, if we talk about the third option, where a player can start with this middle position, then this was the third possible moves by the first player. So if we take the third possible move, then we need to analyze what the option opens for the second player. So obviously, this is one option where it is unique and it has no other parallel thing. Or if it covers here, that is similar to this. Or if it cover here, then that is similar to this. Or if it covers here, that is similar to this. Or if it covers here, so that is a unique position. So let us check. So this is one option, this is second and third option, this is fourth and fifth option, this is sixth and seventh option, and this is eighth option. So what we have seen for the first phase, we have 3 different moves. With respect to that, at the next level, we have for the first situation we have 5 different moves. For the second situation we have 2 different moves, and for the third situation again we have 5 different moves. So subsequently, if you try to draw the overall situation afresh, then initially you can check that this is the board position from where the root level we are starting. So here the cross player will take move. If we try to draw the game tree, so this is one possible move, this is another move, and this is the third option for the cross player. Now further, whenever we have the second player to come. With respect to this, already we have seen that one option can be this and one option can be this. So by this we cover all remaining 8 positions. Now if we try to expand the first one, this one, then here we have to draw 5 subsequent levels. What are those 5 subsequent levels? So since space is a constraint, so let us check if we can draw. So this is one option, another one, if this is one option, another one, since x is here, this is one option, this is the third option, another one, since this is one unique position, and the fifth one, so this. So these are all possible 5 different moves which can be expanded with respect to this level. Here already we have drawn these 2 possible moves. Simultaneously I am not drawing, but you can expand these also, which has 5 different levels which are already explained. In this way, each of these board positions will further be expanded at subsequent level. So you can expand the game tree up to a certain level and you can see how the overall board covers up all the possible evaluations. Now finally, each of these board positions can be evaluated based on one particular equation, which is the board evaluation EP. So in this board evaluation EP, you can see the equation suggests the number of ways open for X minus the number of ways open for O. Means the number of ways X can win the game and the number of ways O can win the game. So always we will see that X try to keep maximum possible options open to win, where circle will try to minimize the possible options for winning. So let us try to explain that these two terms, the number of ways X can win. So we will try to elaborate on number of ways X wins. So when this is the situation, so let us see that what are the ways by which X can win. So this is one. If in this direction all are open, if X can somehow manage these two X's, so in this direction he will be able to find out a winning strategy. This is also an option. We'll be able to find a winning strategy. This is also an option. Since all are open, we can assume that somehow X will be able to manage its marks over here. This is one, two diagonals, and this one, and this one. So altogether, if we try to find out a board, a clear board, so this is one way. Now, let us change the color of the pen. So this is one way, this is one way, this is one way, this is one, this is one. Simultaneously, this is one, and this is one. So 1, 2, 3, 4, 5, 6, 7, 8. So altogether, when the board is empty, one player can have 8 different ways of winning opportunities open. Now, subsequently, when the second player will try to come up, with its move. Suppose X has given it over here. Now the second player, it has marked the situation over here. So now how I can analyze the board position? So obviously once this circle is marked, all the board positions, once the circle is marked, all the board positions are now not open for X. So let us check how many ways X can win after this circle is incorporated in this particular location. So in future we may not know, circle may not be there, so X is still open in this direction, X is still open in this direction, X is still open in this direction, X is open in this direction also. So X is open in this direction also, X is open in this direction also. So altogether what we can see that 6 different options are open for X. Now at the same time we will be also interested to see what are the ways by which circle can win from this particular situation. So this is one option for circle, this is one option for circle, 1 2 3 4 5 and this many, because this diagonal is blocked due to X, and this particular line is blocked due to X. Also this particular line is blocked due to X. So X has already blocked 3 different options. Altogether in a board there can be 8 different winning strategies, and here we can see circle can win in 5 different ways. So now if we try to analyze this particular board which we taken as a reference, that what is the evaluation factor EP for this board. So EP for this board is the number of ways X can win, 6, minus the number of ways circle can win, 5. So EP for this board is 1. Similarly, for in a game tree of tic-tac-toe, we can evaluate each and every board position and find out the values. Once the values we find out, then we can expand them or apply over there the minimax strategy at least to find out what are the ways by which either X or circle can win. Now to proceed further, over here what we can see that in minimax algorithm we need to analyze the all possible leaf nodes level in order to find out the root value of a game tree. Sometimes for a bigger game where so many branching will occur and if the depth of the game will be more, in that particular situation simple minimax strategy may not work properly, and in that case we have a thresholding concept, and that thresholding concept is based on the alpha beta cutoff strategy, where as you can see the maximizing node puts the lower threshold and the minimizing nodes puts the upper threshold. So maximizing node when it puts the lower threshold, on the basis of that if we try to omit the evaluation of some nodes, that omission is called alpha cutoff. And similarly with respect to the minimizing node, if we try to omit some of the node evaluation, that is called beta cutoff. So let us try to have a better understanding in order to this alpha cutoff and beta cutoff slides. Say we have a maximizing node over here, and within that maximizing node at the subsequent level we have two minimizing node. Now their value is 3 and say 10. In this particular case, whenever we will select this particular node, just by selecting the first node and evaluating this, we can say that this maximizing node will always return some values greater than equal to 3, which means since we know the maximizing node always tries to maximize the value out of its option, so once we get on first option as a 3, so we can always ensure if the subsequent options can have better value than 3, then that will be chosen by this node. But if that has some lesser value like 2 or 1, then that won't be selected over here. So this node will always return at least 3 or anything bigger than that. In this case, the right hand side node is 10. So it will return 10 or it will select red, which is greater than 3. Now, similar concept is also applicable for the AND node. Suppose in this AND node, we have some values like this, 5 and 10. So when we will evaluate 5, we can say that this particular node will always return maximum 5 or something less than 5. So if this particular node contains some value lesser than 5, like 1, 2, 3 or 4, so that value will be chosen over here. But if it contains anything greater than 5, like in this case it is 10, so 10 will never come in this particular situation. So it will always return 5 or less. So the basic concept is just by looking at some of the situations or some of the values, we can decide upon that this node will always return certain bigger values of that. Now, let us take this particular portion to understand. So far, we have talked about the thresholding. Now, we come into the concept of cutoff. And in that case, we always need to remember that maximizing node threshold basis comparison, if anything we cut, that is an alpha cutoff, and minimizing node threshold basis comparison, if we anything cut, that is a beta cutoff. So let us take this portion of the game tree, which we have marked over there. So this is 4, this is 13, this is 1, and this is 35. So when we select this, we can say, so this node will always return something less than equal to 4. But yet, here always remain the possibility of finding out some lesser value than 4. So we cannot discard this node from evaluation and we have to check it. Once we check and find it has a higher value than 4, so this node will bang on 4, the value 4 finally. Once this node is getting the value 4, then we can somehow talk about this particular node. Since one of its option is coming as 4, with the concept of thresholding, we can say this node will always return some value greater than equal to 4. Now coming to this node, we evaluate the first one and we see that the value is 1, and this one is a minimizing node. Since this is a minimizing node, so it will always try to return some value less or equal to 1. So anything greater than 1, that won't be returned. Now think about this node. It has already got one option as 4. So accordingly it has thresholded or confirmed that the value that will be returned by this node will be greater than equal to 4. Now coming to the right hand direction, it gets one initial idea that the value is coming less than equal to 1. Now this is meaningless. Even if the value is higher, no way this node is going to return some value better than 1 or higher than 1. So any value which is 1 or lesser than 1 is of no interest for this particular node, because it has already confirmed something 4 or higher. So 4 is confirmed since this particular node is 4. So here we won't go for the evaluation of this particular portion. So how we decided that we won't go for the evaluation? Because of this thresholding, because of this maximizing node thresholding, which is 4. So with respect to the maximizing node, we have compared something and we have discarded a node. So that's an alpha cutoff. You can see over here, that's an alpha cutoff. So these 35 will be termed as alpha cutoff. Similarly, if we take the subsequent portion of the tree, here you can see that once this node has confirmed the value 4, so if we talk about the root node, that is a minimizing node, so that has confirmed some value less than equal to 4, because one of its option is coming as a 4. Now if I draw the right hand side of the tree, here you can see we have a maximizing node. With respect to that, we have two minimizing node. With respect to that, we have some maximizing node with value 9 and 10, which are the leaf nodes, and we have value 1 and 35. So coming down to this, so evaluation in this particular path will come since it is interested to see if it can return some value lesser than 4. So initially we will check this and we will see that this will return some value less than equal to 9. So we will also select this because we are looking for some minimum value. So we will go for this evaluation also. Since it is 10, so the value which is finally consolidated over here from thresholding, that is 9. So once we get 9 over here, as you know, this one is the maximizing node, so it will fix a threshold greater than equal to 9. So now see carefully, this upper level node, it has already confirmed some value 4 or less. This option is no way returning anything lesser than 9. So it is meaningless to check this particular portion. It is meaningless. So we won't check this and this, the leaf node. We will not evaluate 1 and 35. How we decided that? With respect to this reference of AND node, which is a minimizing node. So with respect to the AND node, we decided that we won't go for the evaluation of these two. So we have discarded these two and they will be classified as beta cutoff. Since they will be classified as a beta cutoff, coming to this particular diagram, we can see here we have one alpha cutoff and here we have two beta cutoff. So altogether, this is the idea of thresholding. We will see another example also. So altogether, this was the idea of thresholding, based on which in this particular game tree we find out we have one alpha cutoff and two beta cutoff. So whenever we decide a beta cutoff, always remember that is beta cutoffs are always decided with some reference of minimizing node, and alpha cutoff is always decided with some reference of maximizing node. Now coming back to the slide, if we move further, So here is another example on which we would like to work on. So to find out the number of alpha cutoffs and beta cutoffs where the tree is populated with some more number of nodes. So let us see how we can proceed on this particular diagram. So coming to this diagram, as you can see, so the initial this particular section, so initially we have 10 over here. So what we can write that this will confirm some value less or equal to 10. So we will also consider 11. In between 10 and 11, since 11 is the lesser value, 10 is the lesser value, so 10 will be selected over here. Since we get 10 over here and this one is the maximizing node, so we can always say this will return some values greater than equal to 10. Now once we come here and evaluate this one, so this is 9 with respect to a minimizing node, so we can threshold over here that it will return some value less or equal to 9. Now you check, the maximizing node already has got some value 10, where this node is asking for something less or equal to 9, which is of no interest. So with respect to this maximizing node threshold, we can cut off this 12 and this will be marked as alpha cutoff. This will be marked as alpha cutoff. Now to go further, so we won't evaluate this 12. So to go further, if we say that this maximizing node has got a final value 10, simultaneously it will get its threshold less than equal to 10. Since it is less than equal to 10, so let us come and check that this is 14. So since this is 14, this minimizing node will try to return less than equal to 14. So we will also check this if it gets a lesser value than 14, since we are under a minimizing node, so always it is looking for some minimum value. We will check for that, but it's not, it is 15. So this 14 becomes the final value. Since the 14 becomes the final value, this maximizing node instantaneously it says it can confirm some value greater than equal to 14. Now see, the higher level, it has already confirmed 10 or less. Within that, it is saying 14 or higher. So now it is meaningless to check this portion for this particular node. So with respect to this threshold, we can cut the decision of checking these two. So with respect to the minimizing node, we are cutting down these two. So these two will be termed as beta cutoff. So once we cut down this for the beta cutoff purpose, so this node will get some value that is 10 at the level. So once it gets 10, so this maximizing node at the root level, it will say that it will always return some values greater than equal to 10. So coming down to this level, once we check this 5, so it will tell us that it will return less than equal to 5. Now with respect to this, something value less than 5 is not of our interest, so we can cut this. So this one will become alpha cutoff. And we will say that this node will be returning something value greater than equal to 5. Under that, when we will try to evaluate this. So this is 4. Again it will say less than equal to 4. So once it will say less than equal to 4, to these and these, this is of no interest, this one. So we will cut it out. So this is again an alpha cutoff. So once this is an alpha cutoff and this node confirms some value 5 at least. So this will now become less than equal to 5. Now see, this is a maximizing node. Already it has confirmed some value 10 from this branch. Now this branch is telling that it will return some value less than equal to 5, which is not acceptable to the maximizing node because its primary objective is to maximize the value. So that's why with respect to this maximizing node threshold, this whole portion will be cut off. All these 4 leaf nodes will not be checked and they will come under alpha cutoff. So altogether, if you check the bottom line, you can see that here we get 7 alpha cutoffs and 2 beta cutoffs within the tree. So number of alpha cutoffs over here is 7. That is 1, 2, 3, 4, 5, 6, 7. 7. Number of beta cutoffs in this level is 2. That is this one and this one, 2. So altogether we have 9 cutoffs. 9 is the total number of cutoffs. So total number of nodes we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Out of 16 nodes, we have, by applying alpha cutoff and beta cutoff, we have excluded the evaluation of 9 nodes, which is quite beneficial for the runtime complexity of the overall program, and we'll be only evaluating the remaining number of nodes. So in that case, we'll be only evaluating the 7 number of nodes in total to decide about the final values of the game. So now, coming back to the main slides, based on these particular concept, so you can see here all the alpha cutoffs and beta cutoffs are shown, and in the board we have discussed that how these alpha cutoff and beta cutoffs are decided. Now these are the assignments, one particular assignment where you need to find out the number of alpha and beta cutoff can be there within this particular game tree. So here we come to the concluding portion of today's discussion. This is a final example. We will take the game of NIM. So if you follow the principle of the game, so we will begin with 5 stakes, and that 5 number of stakes will be given to 2 players. So where in particular turn, each player can pick up either 1 stick or 2 stick or 3 stick at a time. The player who will pick up the last stick will lose the game, and we have to expand the game tree. So let us check how we can do that. So initially we have 5 sticks. So we'll be keeping the stack positions over here. So if it picks up 3 sticks, so here we will have 2 sticks remaining. If it picks up 2 sticks, so here we will have 3 sticks remaining. And if it picks up 1 stick at this level, so we will have 4 sticks remaining. So from these 2 sticks, either somebody can pick up 2 sticks, so that will lead to loss because nothing will be remained, and somebody can pick up 1 stick, so that will lead to win because the subsequent player has to pick up that single stick and he will be the loser over here. In this case, if one picks up 3 sticks, so it will be a losing criterion. If somebody picks up 2 sticks, so that will be a winning criterion because 1 stick will be remaining and that will be picked up by the subsequent player. If somebody picks up one stick, so here another two sticks will remain, where the next level of player either can pick up two to lead to the loss, or can pick up one to lead to the win. Similarly, we can expand this particular portion also by terms of 3, 2 and 1 stick and subsequently. So the whole game tree you have to draw. Now it doesn't talk about that which will be the maximizing player and which will be the minimizing player. So either over here, so this is the root condition. So for the first level, if you find it's a maximizing player, so you can mark the values like this, or if you think it's a minimizing player, then you can mark the values like this. And from the bottom level, accordingly, you need to, by applying the minimax strategy, you need to find that which player can win the game. So try to expand the game of NIM in two different ways and try to check whether you can reason out the particular policies. So it was all about the discussion, and within this discussion, hope you are now having a preliminary idea about the strategic game. We have given 3 different assignments to you based on today's discussion. Try to solve it out. Those are a very simple assignment, won't take much time. So try to do that and submit in the Google Classroom to us. And if you have any queries, keep on posting your queries. We will come up with the next videos to clarify your doubts. Thank you for your patience hearing.